Credit card fraud is an ever-increasing problem. According to the Nielsen report in 2022, it amounted to $32 billion a year, with the industry predicted to lose nearly $400 billion worldwide over the next 10 years. As a technologist in the banking industry, I was curious to experiment with machine learning models to see how well they could identify fraud. With this in mind, I found 3 papers that attempted a variety of models to guide my experimentation. Across the 3 papers, a variety of classification models were presented. I did experiment with them all, but the primary model I chose to focus on implemented ensemble learning with a strategy for high recall. As transaction data is highly skewed toward non-fraudulent cases, a high accuracy score can be achieved without identifying any fraud cases. So to properly evaluate the model, we need to maximize the recall score as well. With recall score, as the false negative rate goes to 0, the recall score goes up. With the cost of missing fraud being expensive, it is vital to eliminate as many false negatives as possible. Here's the documented approach I worked with. After training the models and calculating predictions using k-nearest neighbors, linear discriminant analysis, and linear regression, those results are fed into some conditional logic to get the final result. Because logistic regression outputs a continuous value, it is evaluated against the mean predicted value across all the training data. The way the logic works, for each transaction input, if the KNN or LDA prediction is not fraud, and the linear regression prediction is less than the linear regression mean value across all the predictions, then the model returns not fraud. Conversely, if the KNN or LDA prediction is fraud and the linear regression prediction is greater than the linear regression mean value across all the training data, then the model returns fraud. If neither of these conditions is met for a transaction, the result returned by the KNN model is kept as the prediction. Now that I've identified the objective and approach, the next challenge is data. As raw credit card transaction data includes confidential personal data, it can't be published in the public domain. I did identify 2 data sets to work with, both published on Kaggle, and each had their pros and cons. The first data set comes from Vesta Corporation, which is based on real transaction data from their e-commerce platform. So the data includes some realism, but most of it is already encoded and the feature column names are generic to protect confidential data. It was one of the datasets my primary model authors used as well and represented the best opportunity to experiment with realistic data. The second dataset I worked with used a synthetic transaction generator to produce the dataset. So it provides feature name and data transparency, but the realism is suspect. I chose it as all 3 of the papers I surveyed used that dataset when evaluating their solutions. In both datasets, each row is labeled as to whether the transaction is fraudulent or not. The features include things like date, location, and other purchase information related to the transaction. It also includes card information and demographic data about the cardholder. With an objective in mind and some data to work with, let me walk through my implementation. To the best of my knowledge, none of the papers published the actual code used to produce their results, and my project consisted of coding these models from scratch. I experimented with both the datasets I previously mentioned. Pre-processing on the synthetic credit card transaction fraud detection dataset included label coding and scaling each of the features. The pre-processing of the IEEE dataset provided by Vesta was a little more involved. In addition to label coding and scaling, dimensionality reduction was required. The data included a lot of missing values, so the features with the highest occurrence were removed and the remaining features values were imputed to the mean value. Because the data is highly skewed towards the not fraud classification, model bias is a concern. I experimented with 2 techniques to balance the data. I used undersampling of the majority class, and I also tried synthetic minority oversampling to balance the data. Finally, I split each data set into training and testing data, trained the models, and evaluated the results. So how did it do? Here are the results from 1 round of the ensemble learning approach. They are from a run that includes synthetic oversampling of the minority class and tuning the models with hyperparameters I identified from doing a grid search. I'm still experimenting with tuning the models, but you can see here that the full ensemble learning achieved a recall score on the fraud classification of 74% with an overall model accuracy of 75%. Here are the results from the underlying models. The K&N model on its own actually did better with a recall score of 78% and an accuracy of 91%. The LDA and linear regression models both performed at 75% accuracy with a recall score of 74%. In conclusion, the poor performance of both the LDA and linear regression models is bringing down the overall ensemble learning performance. A more sophisticated approach with a focus on feature engineering is probably required. Some future areas I would like to experiment with on this problem are additional feature engineering and time series analysis. Overall, this was an interesting project to take on. I really enjoyed implementing these models. Thank you for watching, and I'm looking forward to seeing what project you took on.